Well, if you can change your freezing point, you can also change the boiling point. Though it kind of works for a different reason. Vapor pressure was the idea that liquid is trying to escape all the time. If I have a container and it has some liquid, water molecules or whatever our liquid is, some of them are trying to break free into the gas phase at any given moment. If you have a bunch of water and at whatever temperature you are, we'll say 10 per second are trying to break free. Well, that is 10 things in solution have enough energy to break free. The energy involved, think about percent and energy for any bulk solution. You get a graph that looks like this. Some percentage has lower energy, some percentage has middling energy, and a small percentage has a very high energy. There is an energy to break free. This is where our vapor pressure comes from. All the molecules that are past that energy, they have the ability to break free if they're at the right spot at the surface at that moment. This means that some number can break free. However, that's for pure water. If just a little bit of that isn't water, if some of it is salt, then some of those things inside your graph, some fraction of those percentage, aren't water. And that includes in the parts that are beyond the break-free energy. That means there's just a few things, if I have salts and other things dissolved, that when they try to break free, they fail. They're not water. So if pure water would have 10 per second leave, if I have a mixture, it might be 7 per second that are water and 3 per second that are something else. Those other things may or may not be able to escape, but the point is they're not water. Some fraction of all the particles that have the energy to escape aren't water, and so they don't have water escape. This lowers the vapor pressure. Effectively, we just have less water escaping per second. Well, remember, where does boiling point come from? If I have pressure versus temperature, vapor pressure has a graph like this. And for water, at 100 degrees Celsius, the pressure that you've gone up to is 1 atmosphere. This is why water boils at 100 Celsius. When the vapor pressure equals the outside pressure, that was when your boiling point was reached. If I have forcefully lowered my vapor pressure, well, then what we end up with is a new graph. We end up with a graph that looks like this. So this would be with salt, or any other thing dissolved in solution. Because it just prevents some vapor pressure, that means at 100 degrees, I am not at 1 atmosphere. I'm not reaching the outside pressure. And so I don't boil. I have to get even hotter before I will match the outside pressure. If you have a solution, it raises the boiling point. So while freezing point got lower because it was harder to lock into a solid, boiling point gets higher because it is harder to have particles escape into the gas phase. And so we have to be even hotter to achieve it. The calculation for this looks similar. The change in temperature of the boiling point is equal to a constant of boiling, which is unique for every liquid, times the molality. The constant of boiling for water is 0.52 degrees Celsius per molal. So that 1 molal solution from before, we would see a delta T 0.52 degrees Celsius per molal, 1 mole per kilogram of solvent solution, 0.52 degrees Celsius. Well, it starts at 100, so it'd be 100.52. So in a kilogram of water, so about a liter, if you put 1 mole of a chemical in, you will raise the boiling point by about half a degree. So if you've ever heard the thing when you make pasta and you put a little salt in the water, that it's supposed to make it boil higher, sort of, but when you put a pinch of salt into probably 2 liters of water in your pot, you're not raising it by much. The salt's just for flavor. It does, in theory, raise it just a little, but truth is, cooking on the lower floor of your building will have a bigger effect on your boiling point than the salt did. Nonetheless, we can change it a little, and in certain situations, this can be pronounced. If anybody's ever had a chance to go to Yellowstone, see the geysers and the like, some of the springs and the pools and the geothermal activity there can have water into the 120, 130 degrees Celsius, where it's not boiling. There are so many salts dissolved that it has caused the boiling point to have to rise 30-some degrees before it can successfully boil. There's just that much salt blocking the liquid from escaping. There's one other property that comes up, but it's really not so much of solution as it is of the chemical that was dissolved. And this is electrolytes. Electrolytes are things that break into ions. So if I have NaCl, if I have 1 mole of NaCl in 1 kilogram of water versus 1 mole of sugar in 1 kilogram of water. Well, at first we would expect that these would be 1 molal. And for the sugar, you're right. But for sodium chloride, remember what sodium chloride when it's dissolved really looks like. It looks like a sodium plus and a Cl minus, and they're separate. They're independent. When sodium chloride, when any salt, dissolves, its ions start to separate. This means you actually have multiple particles. 1 mole of sodium chloride really becomes 1 mole of sodium and 1 mole of chloride for 2 moles of stuff. The solution ends up being somewhere between 1 molal and 2 molal. Some salts are better at fully separating, some mostly separate. But in theory, you could have a 2 molal solution for only putting in 1 mole of sodium chloride. If all of the ions successfully separate, that's 2 moles of stuff. 2 moles of things preventing water from freezing well, 2 moles of things at the surface preventing water escaping to make the boiling point change. It is the number of things that affect colligative properties. Doesn't matter the species, it is the amount. And so electrolytes, things that break apart into ions, they can have an outsized effect for what we'd normally think. So this is part of why salt is so good for de-icing. You could throw sugar on your path, but it will have nowhere near the effect that salt will have for de-icing your pathway. So just one little extra bit. It really comes down to the amount of things dissolved, and we have to recognize that salt compounds tend to break into multiple particles, where organic compounds like sugar tend to stay as one molecule.